We're going to do 8.5 today. Main topic of this is called expected value. It's pretty quick, pretty straightforward. We won't be here super long. I'll go through a few table examples and then we'll do some word problem examples. Before we can start, we need to review what a random variable is. It is a function that assigns a numeric value to each simple event in a sample space. For example, I roll a die and the random variable could come up to be 1, 2, 3, 4, 5, or 6. Those are each different outcomes that could occur for that sample space, that event that I am performing. What you can do is you can create a histogram, which is a graph of the probability distribution. Basically, all that's saying is you're going to draw a bar for each of the different events and their corresponding probabilities and determine what happens with the shape of that. Clearly, in a roll of a die, every single outcome is the same. So all of them would be at the same height. And what we would have would end up being a nice little rectangle as a graph. We had 1, 2, 3, 4, 5, let's see, 6. That is different for different scenarios. Sometimes when you graph them, it'll be bell-shaped. Sometimes if you graph them, it may be skewed one way or the other. In the end, not going to worry about that a whole lot. We are going to talk more about what is called expected value, or the expected average we would see happen from the experiment. Kind of like your long-term results. Are you going to have a positive result? Are you going to have a negative result? And what is that result going to be? There's a formula on the bottom of the screen here that shows you how you calculate your expected value. Expected value is found by taking the individual value times its probability for every single piece that you have. Take every individual times its probability, take the second one times this probability, the third one times this probability, all the way through, and then you're going to add all of those together. Another way to think about this is kind of like a weighted average. Each value has a different percent, a different weight. So when you multiply the two, add them all together, you're going to get your overall expected average. So we'll start straightforward with tables like this. You will just see 2 rows or 2 columns, however they want to draw it. This is drawn in rows. The top row is your value, and the second row is your probability. So all we have to do to find the expected value, what I like to do is I kind of like to create an extra little row here of where I multiply these 2 values together and I write it there. So xi times pi. So all I do on the side is I take each x and times it by its probability. So if I take -2 times 0.3, that gives me -0.6. 0 times anything is 0. 2 times 0.4 is 0.8. And 4 times 0.1 is 0.4. The first step, multiply each x with its probability, and then we're going to go through and sum all of those together. So add all the way across here. And if I do that, I will get 0.6. I'm going to kind of skip around. This one just takes those same values, -2, 0, -2, 0, 2, and 4, and gives them different probabilities. I'm going to go to the next example just because we've seen one that looks exactly like that. And the process is going to be the same for every single example we do today. So I'm not going to have to do a bunch of them for hopefully to catch on. So let's say we are given the next table. The values are -5, -3, -1, 0, 1, 2, and 3. So those are the different outcomes for whatever event I am performing. And then below that are all the probabilities. So -5 happens a tenth of the time. So if I multiply -5 times 0.1, I'm going to get -0.5. -3 happens 5% of the time, or 0.05. So if I multiply those together, that's going to be -0.15. -1 happens 40% of the time. So -1 times 0.4 is -0.4. 0 happens 15% of the time. So 0 times anything is 0. 1 happens 15% of the time. So 1 times 0.15 is 0.15. 2 happens 10% of the time. 2 times a tenth is 20. And 3 happens 5% of the time. So 3 times 0.05, 0.15. So once I multiply them all, I will add them all together. And you may see that some of them actually cancel out. So like the -15 and the +15 cancel out. In the end, your result is -0.55. Makes a little more sense when we get into practical problems here. It says the following table gives the probability distribution of the number of packages in thousands handled by a shipping company. Find the expected number of packages handled on any given day. So basically what happens is they tracked over however long how many packages they delivered every day. 4,000 packages were delivered in a day 30% of the time. 8,000 packages were delivered 5% of the time. 12,000 packages 10% of the time. 16,000 packages 30% of the time. And 20,000 packages 25% of the time. That's what this table is telling me here. So what I can do is then, instead of looking at each individual day, I can calculate the average number of packages we would expect to deliver on any given day. That is what expected value is giving you. So if we do that, multiply the number times probability, 1.2. 8 times 0.05 is 0.40. 12 times 0.1 is 1.2. 16 times 0.3 is 4.8. And 20 times 0.25 is 5. I will then add all of those results together and get 12.6. So what this is telling me is on any given day, the average number of packages delivered is 12.6 thousand, or 12,600. All right, let's see. We'll do one more real world example here, and then we'll look at some where we don't get the table to start with, where we're going to have to create our own table. So this table says the probabilities based on probabilities for the numbers of days of absence for students in a math class each semester. So 0 absences happens 10% of the time, 1 absence 50% of the time, 2 absences 10% of the time, 3 absences 20% of the time, 4 absences 10% of the time. So 10% of the students are absent 4 days, 20% 3 days, 10% 2 days, 50% one day, 10%, they come every day. So we can find the overall average. 0 times anything is 0. 1 times a half is a half. 2 times a tenth is 2 tenths. 3 times 2 tenths is 6 tenths. 4 times a tenth is 4 tenths. Add those all together, that's 1.7. So on average, a student will have 1.7 missed days in math. There are going to be a few times where you do not get the table and you will have to create it. For this first one here, it says you draw and keep a single bill from a hat that contains a $5, $20, $50, and $100 bill. What is the expected value of the game to you? Basically meaning if I play this game on repeat 1,000 number of times, what's the average money I'm making each time I draw? So our outcomes are, I can pull a 5, a 20, a 50, or 100. Okay, next I have to figure their probability. Well, there's a single one of each of them. So there's a $5, a 20, a 50, and 100. There are 4 bills total, 1 of each, meaning the probability of each of these is 1/4. So then all I'm going to do is multiply each value by a 4th, 0.25. It's going to give me 5, 50, it's 12.5, and 100 times the 4th is 25. So add those two together, 25, 30, 40, 43, 75. Okay, so on average, every time I draw, in the long run, I would expect to make $43.75 every time I play the game. Now, the expected value isn't one of the actual values, because it's talking about different things. It's not saying, what number am I actually drawing? What am I actually earning on draw 5? Well, I may only earn $20 on draw 5. Expected value is telling me in the long run, on average, what is happening. Next one says you draw a single card from a standard 52 card deck. If it is red, you win $50. Otherwise, you get nothing. What is the expected value of the game to you? Okay, so my outcome is either going to be red or black. Now, neither of those are numbers, so that is not the X or the P value. It is just the outcome that I draw from the deck of cards. If you draw a red, you win $50. So what happens when you draw a red is you get positive $50. When you draw a black, you win $0. Half the deck is red, half the deck is black. Then if I multiply, 50 times a half is 25, 0 times a half is 0. So on average, I would expect to make $25 every time, right? I would win 50 and then I would win nothing. So in the average, if you average those two together, it's 25. You would expect to draw a red half of the time, a black half the time, and make $50 half of the time. All right, let's try. I think I've got, yep, these are the last two. Two coins are flipped. You win $2 if either two heads or two tails turn up. You lose $3 if a head and a tail turn up. What is the expected value of the game? Okay, so what I need to do is I need to write my outcomes first. So I can flip a head with a head followed by a tail followed by a head, or a tail followed by a tail. Those are my outcomes. Now, what happens is I earn, or I will go up $2 if it's two heads or two tails. So I get positive $2 for head, positive $2 for tail. It says you're going to lose $3 if you get a head and a tail together. So -3 for head, tail, -3 for tail, head. Is flipping a coin a consistent split even probability? You have the same probability of getting a head as you do a tail. Yes. So every single one of these outcomes has a fourth of a chance of occurring. 1/2 times a half makes a fourth. 1/2 times a half makes a fourth. So this one's going to give me positive 50 cents. This is negative 75 cents, negative 75 cents, and positive 50 cents. So in the long run, on average, I am losing 50 cents per game. And that should make sense, right? If you look at the beginning here, I gain $2 on two of the outcomes. I lose $3 on the other two outcomes with equal probabilities. So it makes sense that I'm losing money in the end. So one thing that you can use expected value for is to determine if you have a fair game. So a fair game would come out to be an expected value of 0. It means that whoever plays, dealer, house, whatever, sorry, house players, in the end, it's a wash across the board. In this case, if you're playing this game, you are losing out. And whoever is the one running the game is winning. They are going to be making money off of you. So this is not a fair game. Expected value of 0 means fair game. Okay, so we are going to use that concept then to help us with this last problem. You win, single die is rolled one time. You'll win $5 if a 1 or 2 turns up, $10 if a 3, 4, or 5 turns up. How much should you lose if a 6 turns up in order for the game to be fair? So we can roll a 1, a 2, a 3, a 4, a 5, or a 6. These are the outcomes. They are not the amount of money I am making. They are not the X. I gain $5 for a 1, $5 for a 2. Thank you. Whew. I gain $10 for a 3, $10 for a 4, $10 for a 5. And this is my unknown. I want to figure out what I need to have here in order to make this a fair game. Well, rolling a die is a fair equal probability distribution. There are 6 sides of the die, so each side happens 1/6 of the time. So let's see, if I start multiplying here, this is going to give me roughly 83 cents. 83 cents divided by 6. $1.67, $1.67, $1.67. I'm rounding. And this is 1/6 x. So we know that in order for this to be fair, if I sum all of these, it has to equal 0. So if I take 83 cents plus 83 cents plus $1.67, 1, 2, 3 times, that gives me a total of $6.67 plus 1/6 x has to equal 0. If I want to solve for x, I'm going to subtract the 667 to the other side. I'm going to come up here for those of you in the back so you can see it. So negative 667 equals 1/6 x. To get rid of a 1/6 in front of an x, I would divide by a 6th, but we don't really like dividing by fractions, so I can multiply by the reciprocal, 6 over 1. So negative $40.02. So rounded nicely would probably be about negative $40 if I roll a 6. So gain $5 if I roll a 1, $5 if I roll a 2, 3, 4, or 5, I gain $10. I'm going to lose $40 if I roll a 6. Here's another way to double check it. 5 plus 5 plus 10 plus 10 plus 10. It's 40. Because they are equal probabilities, this has to be negative 40. Again, I only got that 2 cents extra just because of my rounding down here. It was 0.66666 repeating, 0.33333 repeating. So my rounding did impact my final result just a little bit. Hopefully that is easy enough for you to understand the process. You have one thing that you are going to do for me. It is your quick check. It is called the roulette expected value. Generally, I've done this one in the past where I have you like work in groups just to kind of work on this together, and then you can upload it. So yes, I've got 2 minutes. I think I can make it. You're going to do a Google search to find the roulette wheel and then create a table of probabilities to land on red, black, and green. So you'll write your outcomes are red, black, and green. You're going to fill in the values for winning and losing per outcome, assuming you're going to bet $1 on red. So if you bet $1 on red and you spin red, you're going to win $1. But if it comes up black or green, you lose that money. Okay? You're then going to use that image to determine the probability. What probability of the wheel is red, green, and black? To find your expected value when you bet on red. You'll then change the scenario, and we're going to bet on a single number. Betting on a single number is called a 1 to 35. There's 36 numbers on the roulette wheel. So if you bet $1, you earn $35. You win $35 when you get that number, which means you're going to lose your $1 if any other number comes up. So you're going to create a new table for getting a 5 or not a 5, knowing that you're betting $1, earning $35 if that 5 comes up, finding the probabilities, find your expected value, and then talk about what do these answers mean? Does the saying hold true that the casino does, in fact, always win? Do they always have the advantage? Okay. So if you want to work together, you can do that. If you want to do it on your own, have it set to be due tomorrow night. So if you want to work here, cool. If you want to be done and work on it at home, you can also do that as well. I'm here if you want me to check your work.